We're now going to look at an alternate form of the complex velocity equation, or the general complex velocity equation. Let's actually start though with the equation that we developed earlier that relates the circulation to the net flow to the complex velocity. So that was gamma minus I lambda is equal to the integral, or the negative of the integral, over some closed curve of w z dz. Okay, so this was our relationship that we developed that showed how the circulation and the net flow, that's the capital lambda there, are related to the complex velocity. And also let's write out our equation for the complex velocity in general form. In general form, we can say that the complex velocity around any arbitrary geometry can be written in a Laurent series expansion, which we can write as v infinity e to the minus I alpha. That's the constant out front, plus the summation from n equals 1 to infinity of some coefficient a n, and those can be complex coefficients, over z to the n. And actually this first term is n equals 0, where it's z to the 0, so it's just 1. So this is just a complex constant out front, and then we have the summation of the other terms in the series. Okay, so let's look at just a 2D geometry, and this can be any 2D geometry. I'm just going to draw an airfoil just because, but this equation here will fit any two-dimensional geometry where the singularities are centered at the origin, and then we could come up with coefficients that would make the flow around this, or the surface that we're interested in, a streamline of the flow. Okay, so I'll just draw this. We've got some flow around this. And so now let's look at this equation here and compute the circulation and the net flow as a function of this very general solution for the complex velocity. And to do that, and to make it simpler, we're actually going to see, we could look at any closed form or any closed curve around this geometry, right? So we could draw any kind of a curve around this to compute the circulation and net flow around this geometry. But to make it simple, we'll make that curve a perfect circle. And I won't be able to draw a perfect circle, but I'll try something like that. So there's our perfect circle that we're going to use for our for the integral here. Okay, so now if for that perfect circle, we have a couple definitions, and that is, see, we need to integrate in z dz. So we're going to walk along this surface, and so every point along that surface is defined as z equals capital R for the radius of that circle, which is simply large enough to enclose the geometry of interest, e to the I theta. And then we can differentiate that and say that dz is I r e to the I theta d theta. Okay, so we can now plug the dz here in for that dz there, and then this z in for the z's in this Laurent series, and then of course use the w in that equation up there. And what we'll get is something that looks like this. So gamma minus I lambda is equal to the negative, the integral from theta equals 0 to 2 pi, because we're integrating around a circle now. And so we're going to plug in to w, we're going to plug in r e to the I theta for z. And then we multiply dz on the outside, which is I r e to the I theta d theta. Okay, so this is our integral that we'd want to work through, and then and then we'd plug in our w equation now into that where we've evaluated it at re to the I theta. And it turns out if you do that, you end up with a bunch of terms that look like this. We're going to get a bunch of terms that have an ei to the n 2 pi, because we're integrating from 0 to 2 pi, and n is our this summation here for each of these terms. So we end up with a term that looks like this, and it just so happens that that equals 1. Okay, and so that greatly simplifies this, and it turns out that the only term left is a1. All of the other terms in this infinite series actually drop out once we integrate them from 0 to 2 pi. All of them drop out except for a1 here. Okay, and so what we get there is that lambda minus I, or gamma minus I lambda, is equal to negative I 2 pi a1. That's what we'll get if we work through that. So that's pretty incredible. And we see these types of things happen in aerodynamics, where when we put these things in infinite series, or when we do a change of variables into a Fourier sine series, for example, and do a summation over those, this is a very common thing, that we get it in a form where all of the where a bunch of the terms drop out, and we're only left with one that matters for the particular thing that we're looking at here, which in our case is circulation and net flow. Okay, so we took the integral of w of z, which was this general form of wz, and it turns out that when we do that, only the first term matters for the circulation and the net flow. Now, other terms may matter if we were looking at other things, right? But for the circulation and the net flow, it only depends on a1. So what we can do is actually rewrite wz in terms of the circulation and net flow. So we'll just rewrite this equation here, and instead of an or the a1, we're going to swap out these values here. So we'll substitute that in for a1, and then we'll keep the rest of the terms. So that means that in general, wz, our complex velocity, can be written as v infinity e to the, that's a minus I alpha, plus, and then that a1 term, once I solve for it, I'll have a lambda plus I gamma over 2 pi z, and then plus the rest of the terms in the series. So from n equals 2 now to infinity of a sub n z to the n. Okay, so this is now our new general form of the complex velocity, where instead of a1, we now have it in terms of the circulation and the net flow.